Okay, technology and data-driven collaboration, archaeological practice in the 21st century. Archaeology places a great reliance on the relationships between data, interpretation, practice and theory. We undertake a lot of experiments or excavations or data collection exercises which provide us with evidence. And the more of these experiments we undertake, the more evidence it produces. And we can use theory to join the dots up between these bits of evidence. And in many respects, theory constrains how that evidence is collected in the first instance. But there are competing theories to explain this evidence. And as we gather more, we can start to eliminate some of the demonstrably incorrect theories. We also understand that all of these theories make assumptions, and those that are making the fewest assumptions are more likely to be true. So we tend to focus on those theories. And this allows us to get as accurate a picture as we can. May not completely reflect reality, but it's closer than competing explanations. However, we're archaeology, and our jigsaw has many, many missing pieces, and so there's no single reality. We have a conceptual reality based on different contextual viewpoints, so different theories allow us to reconstruct the data that we use to argue different cases. And we get this data from a variety of different environments. So excavation, where we have plans, context, artifacts, ecofacts, soils, sections. Moving up from excavations to different scales, you can look at landscape analysis, of geochemistry, geoprovenancing, a whole heap of other techniques. And essentially, this data, practice and theory forms a hermeneutic loop, and through which individuals go through phases of interpretation and synthesis. So we have a dynamic knowledge acquisition process, and feedback between theory and practice allow us to start to test and revise these models. And the interpretation itself is not conducted in a vacuum. It's conducted by people, and they bring their own experience and philosophical position to this. It's also mediated by mood, weather in the field, if it's too wet. The recording systems and the theory that you use, as I say, constrain or liberate what you do. And from this, we create two broad products of primary data, the excavation records, remote sensing data itself, and decoupled synthetic data or reports as well. So site reports, information held in site monuments or national monuments records. And we end up putting these into silos. So each of the different local authorities and national agencies have their own data repositories. Now there are issues about getting access to that both in real time or in digital and in analog. Some are behind paywalls, some are behind bureaucracy walls. But ultimately, people do want to help other people get access to this information. So you have this battle between the formal and the informal. But it all has resulted in what English Heritage in 1995 referred to as the little used and inaccessible data mountain. All of these little bits of information that percolate down onto our corpus have limited impact on how it's shaping the nature of the data landscape and the interpretive landscape and the theory landscape. The links between them all aren't as solid as they should. And this has an obvious impact on decision making. We're into this Rumsfeldian area of the known knowns, the known unknowns, and the unknown unknowns. The known knowns are the data that we know about and we can actually access and can be there in a timely way to influence the decision making process. The known unknowns is stuff that we know exists, but we can't get it. It's too far away. It's held in a repository, or the bureaucracy won't let us in, or we've got to pay for it, and we don't have the money. And then there's unknown unknowns. The stuff that might actually have a bearing on our problem, but we don't know that it exists, and we don't know that it has any relevance. The main issue here is that what we want to do is to start to maximise the knowns. We already have the stuff we can get access to. We want to enhance the stuff that we can't get access to, so that we can have an improved decision-making process. So this is broad context from which DART was commissioned. And DART has really been looking into the dynamics of seeing beneath the soil. We've been looking at improving prospection techniques. So, for example, in the past, a ditch is dug. Over time, it's abandoned and fills up either through natural or anthropogenic purposes. Someone might fill it up, and then it starts to stabilise, and then it's actually reincorporated back into the landscape. It's buried in the middle of a field, for example. Now, people undertake archaeological prospection, want to find where this is, and so we can use a variety of different techniques, either looking directly at the soil itself, looking at variations in topography, looking at variations in crop height, crop colour. All of these different techniques reveal different contrasts, which allow us to start to postulate that something may or may not be under the ground. But these contrasts change over time. So what DART has been looking at is trying to get a better scientific handle as to how these contrasts change, so that we can deploy tools and sensors more effectively in order to detect them. And to do this, we had two broadly different monitoring areas. There's Diddington to the east of England, drier part, Hart Hill to the west, and both of these areas have a close proximity to heavy clay soils and then better draining soils. And we installed a whole range of different sensors to look at weather and temperature and soil moisture over known features and around known features. And we also did localized geophysics monitoring and took spectroradiometry surveys to look at spectral reflectance for the remote sensing, or the aerial remote sensing component. So here's an example of geotechnical. We took a whole heap of soil samples so we could look at the nature of the soils and then tie that in with variations in soil moisture and temperature, so we could equally look at percolation. These probes were embedded, buried, measured for over 14 months in every case, and recording pinging measurements every 15 to 30 minutes. So we've got a very longitudinal data set. At the same time, we were undertaking regular geophysical monitoring using a variety of different geophysical techniques, approximately on a monthly basis, so we could look at how those contrasts varied over time and then map them to what's going on with the environmental change. Similarly, we were looking from a crop and soil monitoring perspective, looking at the spectral reflectance. Here we were primarily dealing with LiDAR and hyperspectral data, but here's David using a spectroradiometer to produce these spectral curves that are showing differences in crop reflectance at different stage in the growth process. And all of this was to start to increase evidence-based decision making, so we can take the data that we've collected from DART and start to not only use it to look at improving prospection techniques as they currently stand, but also to improve the whole issue surrounding decision making as a whole, so risk determination, policy determination, and landscape management, and also reuse in different areas. And that's really going to be the major focus for this talk. DART is a large project. We have 25 heritage, industry and academic partners, and the best way to keep everyone informed was to adopt an open science philosophy, and we stated in the application that wherever practical, all data will be in the public domain as soon as possible in accessible repositories. In theory, this will allow the science to be dynamically shared with colleagues throughout the world, so the arguments whether we would improve the scientific process, improve results, improve impact, have more of those wow moments where the penny drops. We had Cameron Nayland, who's currently now the Advocacy Director at the Public Library of Science, helped us through this process, and he's been working in the open science domain for a number of years. So this required a corpus of open and accessible resources. So we're dealing with open data, potentially linked data, open methods, open processes, open licenses, which is very important, but ultimately ending up with placing all of this science within a societal context. We were an early adopter of this, particularly in the heritage sector. In 2012, it got a real big boost as the Royal Society produced Science as an Open Exercise, which stated that open inquiry is at the heart of a scientific enterprise. Publication of scientific theories and the experimental and observational data on which they are based permits others to identify errors, to support, reject or refine theories, and to reuse data for further understanding and knowledge. Science's powerful capacity for self-correction comes from this openness to scrutiny and challenge. This is a very, very powerful statement, and it helped a lot when we were trying to explain what we were doing to other organisations. At a basic level, open science does not equal open access. Open access has been getting all of the press coverage at the minute, maybe your green open access within your institutional repository, or gold open access where you're paying a traditional journal to make your paper freely available. I mean, it's great, it's making synthetic derivatives of publicly funded research publicly accessible, but open science does more than that. It's making the objects and the processes of research available. So it's the data elements, it's the algorithms, it's the models that you're using to transform data into information are being made available. So it's those bits that are normally inaccessible from the publication. So you can actually start to peer review the full scientific process and not just a synthetic paper. And so this is much more about engaging communities in analysing and collaborating on future areas. So it's not just talking about what you do, it's engaging people to come in and help you do what you do. Significantly different. So, as I say, it's about engagement, it's about data, it's about collaborations, serendipity, science and impact. From a data end, we're starting to talk about dealing with dynamic resources. It's not just archives anymore. It's resources which can change over time. And also releasing stuff which are in static archives, we start to reduce the data matter and make accessible many of these inaccessible data sets. For example, in archaeology, very few archaeologists get access to hyperspectral data. It's very expensive. It's kind of firewalled. We've made ours available. We'll enhance it with teaching and learning resources. That should have a dramatic impact on the next generation of archaeological remote sensing students. We start to look at the workflows and start to use Linus's law, where given the fireballs all bugs are shallow, and apply it to data. Our workflows can be peer reviewed because these people are looking at them. That will reduce in better models. That will increase trust, provenance and credibility. So if we move into this semantic web scenario that Tim Berners-Lee is talking about, trust is part of the framework. We have open processes, so we're revealing our underlying approaches. This is really important. It generates that trust. We have an increased understanding. We're demonstrating transparency and reuse, which means, we're demonstrating transparency, which will improve reuse because people know how to reuse our stuff. It will make our synthetic publications much stronger because people can re-implement the science. It also allows for greater collaborations. Obviously, within DART, we brought together aerial archaeologists, ground-based prospection people, geoarchaeologists, soil engineers to look at this problem. But because we've opened up our data in that process, we've been effectively working with soil mappers, precision agriculture people, geosensor people. We're broadening our collaborative network. That is a good thing. So when we start to bring it all together, we've got more data. We're building more reliable models that actually access the raw rather than generalized data. That should result in better decision making because we've got better models, we've got a better understanding of the process. It's all based on this rich data. It's also easier to be reused and engaged with by a whole range of different stakeholder communities. Reuse is encouraged. Outreach is not just a passive activity. It's not just a lecture. It's a discussion. And this area of serendipity, this free flow of data and ideas. And this is important from the whole societal engagement. It's about kind of refocusing attention. It's getting those people who are specialists to come in and help with our workflow bottlenecks. One of our collaborators is a nuclear scientist who is now running the West Lothian archaeological group. His knowledge of physics far outstrips most, if not all, of the physical knowledge of people on the DART project. Having people like that tied into your workflow who can answer what are complex and difficult problems for you very, very easily is very important. So we're no longer masters of all. We survey. This kind of data demands that we collaborate and collaborate effectively with external specialists. So why do we do this? The EU says so. In respect of citizen scientists, enabling them is not just good for science, it's also necessary for smarter decision making As the technical complexity of policy from global warming to macroeconomic management rises, open science supports open government. And we're all aware how much stock the government is putting in opening up data. The UK government says so, from the Shakespeare Review of Public Sector Information. This data, to optimise its value to society, must be open, shareable, and where practical it should be free. Now this is talking about public sector information. Does academic information fall under the same umbrella? Well, if it's funded by the public, then I would say yes. And we need to start to understand what we're doing here. Are we spin-out companies, or are we undertaking publicly funded research where we have an obligation to the funder? The Royalty Society says so. Recent decades have seen an increased demand from citizens, civic groups and non-governmental organisations for greater scrutiny of the evidence that underpins scientific conclusions. In some fields there is growing participation by members of the public in research programmes as so-called citizen scientists, blurring the divide between professional and amateurs in a new way. Engagement. This is great stuff. And EPSRC says so. EPRC funded research data is a public good, produced in the public interest, and should be made freely and openly available with as few restrictions as possible in a timely and responsible manner. And that's pretty unequivocal. Okay, so what did we do? We built a data repository. It's based on CCAN from the Open Knowledge Foundation. It's a full metadata system. We chose a licensing framework, Creative Commons by attribution, open database license to encourage reuse and to facilitate tracking. We can track the impact of what we've got. We use the Open Archives Initiative protocol for metadata harvesting for a harvesting node, which means that metadata can be re-ingested and reused by other organisations. So a daisy chain effect. So our stuff can be harvested by the Archaeology Data Service, or Europeana. Each of the data has a URI, so it'd be called by web processors. And the repository framework itself has its own API. So here's our framework. We have a look at some of the data sets. So we've got, these are actually, when it says 18 data sets, these are actually collections. So it's collections of data within here. So we have a whole heap of different stuff in here. And we're currently also going through an update on this, so more and more data will be coming in. So having a look at our thermal experiment. Here we have a little bit of information describing what it is. At the bottom here we have a whole heap of metadata, so who the author is, who the maintainer is, what the instruments were that we used to collect it. So an abstract citation, you can cite our data, and this is a snippet that you can put into BibTeX, who we were collaborating with, resource description, a whole heap of stuff, and somewhere in there will be the license as well. I can't see off the top of my head, but you will find it. And here we are, it's showing us where it's actually come from. And these are the data sets themselves. So we have in here video, thermal images, some illustrations, and let's see if we can have a, here we are. Okay, so, and there's a photograph of the scaffolding tower that we're using, and again, this is now specific metadata about that object. And so, as I said, we have thousands of objects like that. So fantastic, we have this metadata resource. This is an area that does require core investment. Dart has paid for this repository on its own, and it's not really here just about dealing with archives. We're dealing with a dynamic corpus of data, as we described in the introduction. We shouldn't be dealing with static information, because we know that the nature of our data changes over time. New knowledge percolates through the whole data infrastructure. We need to deal with that a bit more effectively. Quick aside on licenses, we use Creative Commons by an open data open database, both expect attribution. You can put clauses on these, share alike, non-commercial, no derivatives. These can become problematic because they make the resources less free. They start to segment sects of society who can use this stuff. More importantly, you can have many unintended consequences for reuse and integration. Licenses, if you are going to license in this way, you need to have someone in place who will manage it, when to validate with someone, to field questions. If that's a cost overhead, can you afford it? Examples are that Creative Commons share alike and Creative Commons non-commercial share alike are incompatible. You cannot merge data that are stored in those licenses together. Equally, universities and museums are rarely non-commercial. It's complex as soon as you start to muddy the waters. So if you're going to do this, get advice from organisations like Open Knowledge Foundation. Don't use your gut reaction. We've also produced an integrated spatio-temporal model. This is our back-end unified modelling language. For that, we've exported that to Postgres, which is a database, which means it's easy for people to pull that in their own way. So you can create your own back-end spatio-temporal database. And this is essentially what we're going to use for online data mining and part of a collaborative analysis. Most of our stuff is done under Python. Again, these are all shared under liberal licenses. Because it's accessing data with an accessible URI, there are some possible issues here with the database. There's no barriers to re-implementation. So as an example of this, here's the CSV download. So this is where we can import our libraries. So we're using urllib2, numpy, matplotlib, for those of you who know Python. Here we're going to start to import the data. Here's a citation. Here's the data we're actually going to use. As you can see, it's a Dart portal, and so we'll load that in and we'll print it out. So that's our data as a list as it comes in. It's a comma separated file. We're now going to restructure it so it looks like the 20 by 20 grid that it actually comes through. So we're now restructuring and printing it, and so those are all the numbers. So let's actually plot those numbers at a grayscale. Ta-da! And then we can start to then run some derivatives over this. So Sobel, Laplace, Pruitt, Gaussian minimum filter, and then let's show the, which one are we showing here? It's the Gaussian. So there's a Gaussian filter, and or we can plot them all, which is what we're showing at the bottom. Well, very easily we can change the dataset we're working on. So we're loading in a new dataset, run it through, and we can print it out. There we are. Now the nice thing about this is it's made our whole processing transparent. You can look at the numbers, you can see what we've done with the numbers, and you can see how that impacts on the output. Now if you want to change that or you think we've done it wrong, you can edit it. We have transparency in data process. That's really important. Okay, so get back to the show. So what did we learn? Stakeholders like it, really like it. Generated an enormous amount of goodwill. It enhanced collaborations on our network. Particularly we worked with David Jordan at Mainz, who added extra value to the research we were doing. He came out and undertook further data sampling and analysis techniques to build on what we were doing. So just because we were open, we were able to engage and increase the science impact. Also, it's not just about our domain, it's about outside of our domain. We've been working with the Royal Agricultural University. LiDAR and hyperspectral data is being used to look at carbon sequestration. Some of this will be used to look at the compaction issues in the soil. We've handed over the probes to Royal Agricultural University so that they can continue to get longitudinal data, because it's important for them too. And this creates more collaborations, enhances our network. Data management is placed at the forefront. The project, before the project is concluded, we have all of our data available in a way which is consumable by the Archaeological Data Service. That's great. All the metadata is there. It's not just bolted on at the end. Allows the use of web analysis frameworks. We also found out repositories are expensive and licensing and IP are complex. Significantly, open science is not seen as a universal good by academics. Very few incentives. Our career trajectories are dominated by publication output. There's perceptions of loss of competitive advantage. You can't just sit on your data and squeeze the life out of it. The converse is that you've enhanced collaboration and networks, which are equally good for your career. This perception is that it prejudices PhD novelty and publication viability. Well, possibly, but it depends upon which domain you work in. The thing is that these issues are understood by the Royal Society and other places, but they are also complex and vary throughout the hierarchy in different domains. The thing is they are starting to change, So I don't see this as being a static problem. Within the heritage sector, there's always going to be issues about ethics and who gets access to data. People have this great fear of metal detectorists, for example, or Nighthawk metal detectorists, unscrupulous ones. What about accreditation systems? The Portable Antiquity Scheme has used this to great effect with their data. I think we should be having a much more mature debate about ethics. I'm much more interested in finding out how we can enhance access to data so that local communities can look at community-based stewardship. I don't see us as having the default position of being keepers of a portal. So, what is the future? We need to invest in the infrastructure. We need data and workflow repositories, interoperable catalogues, so the data can move from different places. It's not just a problem for for academia. And I also don't see this as an archiving issue. This is much about dynamic and accessible corpuses of information, or corpi, whatever the word is, plural is. Dart itself, we've got a whole heap of data mining visualization stuff to get on with. We've got all of this great data. We've only just scratched the surface of it. It is a fantastic resource. It has an impact on knowledge-led practice and policy. Last year we put in an FP7 project called Thematic, which was looking at developing new methods for monitoring, detecting and characterising heritage landscapes, their nature, location, state and risk position. So it wasn't just about detecting new features, but it was about trying to find decision-making frameworks which would help for a whole range of different stakeholders and policymakers. This didn't get funded, but we're still working on this, so if anyone's interested in this kind of risk monitoring at a landscape level, feeding into the European Land Convention, please contact me. Also, we're looking at creating a culture of open data and collaborative analysis. We've got this stuff at Dart, let's make it reusable. So, encouraging stakeholders to exploit Dart and other reuses, starting to embed it within the thinking of both educators and policymakers and decision makers and academics. Finding some of the data deposition bottlenecks. We know that geophysics could do better. Providing analysis cookbooks, standard models in which you can simply analyse your data, in open and transparent ways. You know what's happened to the numbers. Encouraging multi-stakeholder interaction. Here you've got hack days where you've got people who have data and people who have a problem and people who have the nous to know how to solve that problem with data but don't know about the others. Hack days are quite an effective way to look at this issue. And we're wrapping those up in an AHRC follow-on fund. So, to finalise, it's a quote from English Heritage. Knowledge is a prerequisite to caring for England's historic environment. From knowledge flows understanding, and from an understanding flows an appreciation of value, sound and timely decision-making, and informed and intelligent action. Knowledge enriches enjoyment and underpins the processes of change. It's great. You can't really, argue against that. However, I would suggest that the more you make things open, the more likely that vision is to come about. Thank you.